Imagine a time, long before the thunder of dinosaurs echoed across the land, before even the first whisper of forests could be heard on the wind. The world was silent above the waves, its surface a barren expanse, untouched by roots or leaves, where only the sun and the elements shaped the landscape. The continents themselves were little more than vast rocky plateaus, their surfaces scoured by wind and rain, utterly devoid of green. No trees, no grass, not even the smallest moss clung to the stone. The air was thick with the scent of minerals and dust, and the only movement came from shifting shadows as clouds drifted overhead. Picture a coastline that seems almost otherworldly. Jagged rocks plunging into endless blue, the boundary between land and sea sharp and unsoftened by any living thing. This was a world that to our eyes would seem stark and alien, a planet in the midst of transformation. The land under a relentless sun was a canvas of stone and silence, waiting for the first pioneers of life to one day arrive. But in this age the true story was unfolding elsewhere. This was the Ordovician Period, a remarkable chapter in Earth's deep history, stretching from 485 to 443 million years ago. It was a time when the surface of the planet was still young, and the forces of geology and climate were shaping a world unlike any that would follow. While the continents slumbered in their rocky stillness, the oceans below were alive with energy and possibility. The sea was the beating heart of the Ordovician, a vast and mysterious realm that held nearly all of the planet's life. These oceans were shallow and warm, stretching across the globe in broad, sunlit expanses. Here, life flourished in forms both familiar and utterly strange, creatures with shells, spines and tentacles drifting and crawling in a world of endless blue. The Ordovician was an age of innovation, a time when evolution experimented with new designs. On the seafloor, new species appeared in a dazzling array, each one a testament to the creativity of life. Over millions of years, the oceans transformed. The once empty seafloor became a bustling metropolis of living things, each niche filled by a new and wondrous form. The Ordovician followed the Cambrian period, which had already witnessed the first explosion of animal life. But the Ordovician was different, more dramatic, more diverse, more complex. It was a time of escalation when the number of marine species multiplied at an astonishing rate. The seafloor became a tapestry of life woven from countless threads of evolution. Scientists call this the Great Ordovician Biodiversification Event, a moment in history when the diversity of marine life exploded, filling the oceans with new possibilities. Life was not just surviving, it was thriving, branching into every available space. Creatures clung to rocks, burrowed in sand, and built intricate colonies on the seafloor, each adapting to its own unique corner of the underwater world. From the sunlit shallows to the shadowy depths, the Ordovician ocean was layered with life. Each level teemed with creatures, some drifting near the surface, others prowling the darkness below, forming a complex web of interactions that would shape the future of all marine ecosystems. But the Ordovician was not just a time of biological change. The very face of the planet was shifting. Continents moved, oceans widened and narrowed, and volcanoes rumbled beneath the waves. The continents we know today were scattered in unfamiliar shapes, drifting across the globe in a slow, relentless dance. The supercontinent Gondwana, a massive landmass made up of what would become South America, Africa, Australia, Antarctica and India, was slowly journeying toward the South Pole, its movement shaping the world's climate and the flow of the oceans. This planetary ballet had profound consequences. Ocean currents shifted, climates changed, and the stage was set for both abundance and catastrophe. The Ordovician began as a greenhouse world, its atmosphere thick with carbon dioxide. The seas were warm, and life flourished in the gentle embrace of the sun. But this warmth was not eternal. As the period drew to a close, the world changed again. Temperatures dropped, ice crept across the land, and the oceans themselves began to freeze. Today, the story of the Ordovician is written in stone. Layer upon layer of ancient rock holds the secrets of this lost world, each fossil a message from a time beyond memory. Fossils are our only window into this distant past. They reveal the shapes and lives of creatures that once ruled the seas, their forms preserved for hundreds of millions of years. These ancient stones tell of a world dominated by sea monsters with long conical shells, orthocone cephalopods, the silent hunters of the deep. They speak of trilobites, armoured and alert, their intricate eyes scanning the seafloor for food and danger. And they reveal the first creatures with backbones, jawless fish gliding through the water, ancestors of all vertebrates to come. The Ordovician is a story of resilience and invention, of life's endless ability to adapt and thrive. In these ancient seas, the foundations of modern ecosystems were laid, and the blueprint for future life was drawn. So let us leave the silent land behind and plunge into the vibrant, teeming world beneath the waves. The Ordovician awaits, a realm of wonders, mysteries, and the first great monsters of the sea. The Ordovician period did not simply pick up where the Cambrian left off. It unleashed a tidal wave of innovation and diversity that forever transformed the world beneath the waves. In these ancient, sun-dappled seas, life was not just continuing, it was erupting in a spectacular display of creativity and adaptation. What unfolded in these primordial waters was nothing less than a biological Big Bang, a phenomenon now known as the Great Ordovician Biodiversification Event, or GOBI. This was a time when the very fabric of marine life was being rewoven, thread by thread, into something astonishingly complex. Over the course of roughly 25 million years, the oceans became a living laboratory of evolution. The number of marine families more than doubled, and the number of genera, those subtle branches on the tree of life, tripled. Every corner of the sea seemed to teem with new forms, each more intricate than the last. Where once the seas had been relatively simple, they now swelled with a riot of life. Coral-like reefs rose from the sea floor, and every available niche was filled by creatures locked in a constant struggle for survival. The ocean became a stage for endless competition, with each species striving to outwit, outgrow, or outlast its rivals. What could have sparked such a dramatic transformation? The answer lies in a perfect confluence of geological and environmental changes, each one setting the stage for the next act in this evolutionary drama. As continents slowly drifted across the globe, vast shallow seas flooded their margins. These new habitats, bathed in sunlight and rich in nutrients, became immense nurseries where life could experiment and flourish. Here, the gentle sway of the tides and the warmth of the sun created a cradle for endless possibilities. Meanwhile, monumental mountain-building events, such as the tectonic orogeny, thrust new peaks skyward. As these mountains weathered and eroded, torrents of nutrient-rich sediment poured into the seas, transforming the chemistry of the water and providing a feast for the smallest inhabitants. This mineral influx acted as a supercharged fertilizer, igniting blooms of plankton that drifted in shimmering clouds. These tiny organisms formed the foundation of the food web, supporting an ever-growing cast of marine animals above them. With this abundance came a surge of evolutionary innovation. As new species appeared, competition intensified. Each creature was forced to adapt, to find new ways to survive and thrive in a world that was growing more crowded and complex by the day. This relentless pressure sparked an evolutionary arms race. Prey animals developed tougher shells, sharper spines, and ingenious behaviours. Some burrowed deep into the sediment, while others curled into tight, defensive balls, hoping to evade the ever-watchful eyes of predators. Predators, in turn, responded with their own arsenal of adaptations. Some grew stronger claws to pry open shells, others evolved more powerful jaws or keener senses, all in pursuit of their next meal. This constant back and forth drove life to new heights of complexity and specialization. Creatures became more efficient, more cunning and more diverse, each one a testament to the relentless push and pull of evolution. The simple food chains of earlier times gave way to intricate webs, where specialized hunters stalked their prey, grazers scoured the seafloor, scavengers cleaned up the remains, and filter feeders sifted nourishment from the water. The result was a world transformed. The seafloor, once a barren expanse of mud and mystery, now teemed with life. Every inch was covered with colonies, shells, and waving fronds, a living tapestry woven from countless forms. Moss-like bryozoans formed sprawling colonies, while brachiopods, shelled animals with a quiet resilience, blanketed the substrate, their shells opening and closing with the rhythm of the tides. Graceful sea lilies, or crinoids, anchored themselves to the seafloor, their feathery arms swaying in the currents as they filtered food from the passing water, adding a delicate beauty to the bustling scene. Among these stationary wonders, a menagerie of mobile creatures prowled and darted. Armoured arthropods scuttled across the bottom, molluscs glided through the water, and the earliest vertebrates, small, jawless fish, navigated the labyrinth of life. The Ordovician seas had become a vibrant metropolis, alive with colour, movement and danger. Here, in this ancient aquatic world, life reached a new crescendo, setting the stage for all the wonders yet to come. In the vast mysterious blue of the Ordovician seas, a silent drama unfolded each day. A world where power was measured in size, speed and cunning, and where the rulers were unlike anything that would ever come after. The thrones of this ancient oceanic kingdom were claimed by predators of astonishing form and ferocity, each perfectly adapted to the challenges of their watery domain. Dominating the open waters were the giant orthocone cephalopods, the undisputed monarchs of the Ordovician deep. Picture a creature with a sleek, elongated shell, straight as a spear, gliding silently through the water. Its body, soft and muscular, trailed behind while a crown of tentacles waved and searched for prey. Some, like the legendary Camaraculus, grew to monstrous proportions. Their shells stretched up to 6 meters long, casting shadows over the seafloor as they passed. These cephalopods moved with a sudden jet-propelled burst, siphoning water through their bodies and shooting forward with surprising speed. Their tentacles, lined with suckers, darted out to ensnare any creature that strayed too close. With powerful parrot-like beaks, they could shatter the shells of trilobites and other armoured denizens, feasting on the soft flesh within. Yet the orthocones were not alone in their reign. The Ordovician seas teemed with other formidable hunters, each carving out their own niche in the ancient food web. In the shallows, the eurypterids, known as sea scorpions, prowled the muddy bottoms and rocky outcrops. These were not true scorpions, but a lineage of aquatic arthropods, their segmented bodies armoured and their movements both graceful and menacing. Early forms like Megalograptus stalked the seafloor, their spiny limbs and sharp pincers ready to seize any unwary animal. Their pincers, large and powerful, could grasp and tear apart prey with ruthless efficiency, while their broad, paddle-like tails propelled them through the water, allowing them to chase down even the swiftest of victims. Some eurypterids scoured the seafloor for carrion, cleaning up the remains of the fallen, while others hunted with relentless energy, a constant threat to smaller creatures. The rise of these sea scorpions marked a new era of predatory mastery among the arthropods, their tactics and tools honed by countless generations of survival and competition. Among the most iconic of the Ordovician residents were the trilobites, their numbers and diversity unmatched in the ancient world. With their distinctive three-lobed bodies, trilobites had weathered the storms of the Cambrian and now flourished, evolving into a dazzling array of forms. They spread into every corner of the sea, from shallow reefs to deep, dark basins. Some became swift hunters, others patient scavengers, and many sifted through the soft mud, searching for morsels of organic matter hidden beneath the sediment. Their eyes, intricate mosaics of hundreds of lenses, granted them a panoramic view of their surroundings, alert to both danger and opportunity. To defend against the ever-present threat of predators, many trilobites, such as the sturdy Acephus, could curl into a tight armoured ball, their vulnerable undersides shielded from attack. Amidst this bustling invertebrate realm, a new kind of creature began to appear: small, jawless fish, their bodies armoured and their movements tentative. These primitive fish glided close to the sea floor, their forms simple and unassuming. Yet they represented a new experiment in the tapestry of life. The earliest among them, like Arandaspis, wore suits of bony armour, their mouths fixed in a perpetual toothless gape. Lacking jaws, they could not bite or chew, but instead drifted and filtered tiny particles from the water or mud. Their feeding was a patient affair, sifting through the sediment for nourishment, always wary of the shadows above. Their greatest advantage was their armour, thick, interlocking plates that shielded them from the crushing jaws and pincers of the sea's top hunters. When attacked by a cephalopod's beak or a eurypterid's claw, these bony plates often made the difference between life and death. In the ever-changing Ordovician seas, these armoured, jawless fish joined the ranks of the rulers, their presence a quiet but significant shift in the balance of power beneath the waves. While the open waters teemed with formidable predators, a quieter yet equally transformative drama was unfolding far below, on the ancient seafloor. Here, in the dim light and gentle currents, a revolution was underway, one that would forever reshape the marine world. For the first time in Earth's history, living organisms began to construct vast, intricate structures, true coral reefs, rising from the seafloor like underwater fortresses. These reefs were not built by the familiar corals of today, but by ancient architects, tabulate and rugose corals whose forms were strange and beautiful. Tabulate corals formed honeycomb-like colonies, while rugose corals, sometimes called horn corals, grew as solitary towers or clustered together in small groups. Alongside them, stromatoporoid sponges, massive, mound-shaped creatures, added their own stony skeletons to the growing reef. Together, these organisms built three-dimensional labyrinths of limestone, stretching ever upward, seeking the nourishing rays of sunlight that filtered down from above. The result was a world of arches, crevices and towers, a living maze that transformed the once flat seafloor into a landscape of endless possibility. These reefs became bustling underwater cities, their nooks and crannies sheltering a multitude of life forms. Every surface offered a place to hide, to anchor or to hunt, while the reef itself provided a steady supply of food drifting in with the currents. The abundance of food and shelter made these reefs magnets for new arrivals, drawing in creatures from all corners of the ancient sea. Over time, the reefs became hotspots of biodiversity, their surfaces and shadows alive with activity. Countless organisms found their homes here, some nestled within the coral branches, others clinging to the sponges, and still more weaving through the maze of stone and life. The arrival of these reefs did more than just provide shelter. They changed the very shape of the sea floor, creating new landscapes and microhabitats. Their massive forms acted as barriers, redirecting currents and shaping the flow of water, while their bulk stabilized the shifting sands of the shallow seas. In places where the seafloor had once been a shifting desert, reefs anchored the landscape, creating havens of stability and abundance. These monumental structures were the result of cooperation on a grand scale. Countless tiny creatures working together, their combined efforts shaping the world around them. In doing so, they engineered the marine environment, creating new opportunities for life to flourish. The reefs fostered ever greater levels of biodiversity, each new arrival adding to the complexity and vibrancy of the ecosystem. Amidst this structured world, a new cast of characters began to thrive, the filter feeders, masters of extracting nourishment from the water itself. These patient creatures made their living by straining tiny food particles from the passing currents, turning the ocean's bounty into sustenance. In the Ordovician, filter feeders exploded in both abundance and diversity, filling every available niche around the reefs. Brachiopods, with their hard shells and delicate feeding apparatus, blanketed the seafloor in dense colonies, their shells opening and closing in silent rhythm. These colonies stretched for meters, creating living carpets that filtered the water above. Bryozoans, or moss animals, formed delicate, lacy colonies that encrusted rocks, shells, and even the surfaces of other living creatures. Among the most graceful of all were the crinoids, or sea lilies, their slender stalks anchoring them to the seafloor. Each crinoid stood tall, waving a crown of feathery arms in the current, ready to snare any morsel that drifted by. With every gentle movement, they captured food from the water, their arms moving in a slow, mesmerizing dance. The rise of these filter feeders had a profound effect on the Ordovician oceans. By constantly removing organic matter and plankton from the water, they helped to clarify the seas. The water grew clearer, sunlight reaching deeper than ever before. This new clarity allowed sunlight to penetrate to greater depths, nourishing photosynthetic organisms and enabling reefs to grow even further down the slopes of the seafloor. Algae and other photosynthesizers flourished, carpeting the reefs and providing even more food for the teeming life around them. This was a remarkable example of a biological feedback loop. As life changed the environment in turn created new opportunities for life. The success of the reefs and filter feeders was not just a story of survival, but of transformation. Life reshaping the very world it inhabited. Each change opened the door for new forms of life, new strategies and new wonders to emerge. The Ordovician seas became more organized, more efficient and more productive than ever before. A thriving tapestry of life, woven together by the silent, ceaseless work of reefs and filter feeders. In these ancient waters, the stage was set for the next great chapters in the story of life on Earth. The biological drama of the Ordovician did not unfold on a static stage. Instead, the very ground beneath the ancient seas was in motion, and the sky above was far from tranquil. The Earth itself was a restless, ever-changing planet. Massive slabs of crust, known as tectonic plates, creaked and groaned as they drifted across the globe, carrying entire continents with them. These continents, propelled by the slow but relentless force of plate tectonics, were on a journey that would reshape the face of the planet. Over millions of years their paths would redraw coastlines, open and close vast oceans, and set the stage for new worlds to emerge. The colossal landmass of Gondwana, destined to become Africa, South America, Australia and Antarctica, was slowly but inexorably drifting southward, inching ever closer to the frigid expanse of the South Pole. Its journey was so gradual that it would take tens of millions of years to complete, yet its movement would have profound consequences for the world's climate and life. Elsewhere, smaller continents like Laurentia, the ancient heart of what would become North America and Baltica. The precursor to Scandinavia and Eastern Europe, along with Siberia, were scattered like islands across the warm equatorial seas. These land masses were separated by vast, deep oceans, their coastlines battered by waves and their interiors untouched by the icy winds of the south. The slow-motion ballet of these drifting continents was the master architect of the Ordovician world. As land masses shifted, they sculpted the flow of ocean currents, redirected winds, and created new habitats for life to flourish or fade away. Among the most dramatic geological events of this era was the tectonic orogeny, a titanic episode of mountain building that would forever alter the landscape. This event began as a volcanic island arc, born in the restless depths of the ocean, drifted inexorably toward the eastern edge of Laurentia. When these islands finally collided with the continent, the impact was slow but immense, unleashing forces that would crumple the crust and raise mountains from the sea. Over millions of years, the collision forced up a mighty mountain range, a jagged backbone of stone that would one day become the ancient roots of the Appalachian Mountains. These new peaks towered above the landscape, their summits shrouded in clouds, their slopes raw and wild. But the mountains' reign was immediately challenged by the elements. Wind howled through their valleys and rain lashed their flanks, beginning the slow but relentless process of erosion. Rivers, swollen with rain, carried vast loads of sand, silt and clay down from the highlands, pouring them into the shallow seas that lapped at the mountains' feet. The waters grew murky with the bounty of the land. These sediments were rich in nutrients, phosphorus, iron and other elements essential for life. As they spread through the seas, they fertilized the waters, sparking blooms of plankton and feeding the explosion of marine diversity known as the Great Ordovician Biodiversification Event. Yet the drama was not confined to the land and sea. Overhead, the Ordovician sky was a stage for cosmic events of staggering scale. Around 467 million years ago, a colossal asteroid, over 150 kilometers wide, shattered in the asteroid belt between Mars and Jupiter. The explosion sent a cascade of rocky fragments tumbling through the solar system. These fragments, some as small as pebbles, others as large as mountains, were flung toward the inner planets. Earth, spinning silently through space, soon found itself in the path of this cosmic debris. For millions of years, the planet endured a relentless bombardment. Meteorites rained down, their fiery trails streaking across the sky, their impact sending shock waves through land and sea. The rate of impact soared to 100 times the usual, transforming the Ordovician world into a place of frequent celestial fireworks. The surface of the planet became littered with L-type chondrite meteorites, their mineral-rich fragments settling into the sediments of ancient seas and landscapes. Unlike the single catastrophic impact that would one day end the reign of the dinosaurs, this was a drawn-out shower of cosmic material. As meteorites dissolved in the oceans, they released rare minerals, subtly altering the chemistry of the seawater and perhaps providing new ingredients for life to exploit. The Ordovician world was shaped by the interplay of these immense forces: tectonic upheaval, mountain building, erosion, and the ceaseless rain of meteorites from the sky. As continents shifted, they redirected the flow of warm and cold ocean currents, creating new patterns of climate and weather. The seas themselves became highways for nutrients and life, their currents swirling around the ever-changing land masses. The rising mountains, battered by wind and rain, sent rivers of minerals and nutrients into the ocean, nourishing the teeming life below the waves. Meanwhile, the rain of meteorites added a touch of cosmic unpredictability. sprinkling the seas with elements forged in the heart of distant asteroids. Life in the Ordovician was never isolated from these changes. Every creature, from the smallest plankton to the largest predator, was shaped by the shifting continents, the rising mountains, and the falling skies. The story of the Ordovician is a tale of constant transformation, a world where the living and the non-living were locked in a dance of creation and destruction, each shaping the other in ways both subtle and profound. In this ever-changing world, the Ordovician stands as one of the most compelling and dynamic chapters in the history of our planet, a time when continents wandered, mountains rose, and the skies themselves seemed to fall. For millions of years during the Ordovician, Earth was a world bathed in warmth and sunlight. Vast, shallow seas shimmered beneath a sky heavy with moisture, their waters teeming with an astonishing diversity of life. Coral reefs flourished, trilobites scuttled across the seafloor, and strange, armoured creatures drifted in the gentle currents. It was a time of abundance, a true marine paradise. The atmosphere was thick with carbon dioxide, 10 to 16 times higher than what we know today. This greenhouse blanket trapped the sun's energy, creating a climate so warm that even the polar regions were free of ice, and the oceans stretched unbroken from equator to pole. No ice caps crowned the poles. Instead, shallow sunlit seas covered much of the continents, providing a haven for marine life to evolve and diversify in spectacular ways. But this golden age was not to last. Subtle shifts began to ripple through the world's climate, setting the stage for a dramatic transformation. The supercontinent Gondwana, a massive landmass stitched together from what would one day become Africa, South America, Antarctica, and Australia, began its slow, inexorable journey southward. Over millions of years, it crept toward the bottom of the world, eventually settling over the South Pole. This new arrangement of continents changed everything. As Gondwana blanketed the pole, it disrupted ocean currents and altered wind patterns. The world began to cool. Glaciers formed, first as small patches of ice, then as vast gleaming sheets that spread across the land, reflecting sunlight back into space and accelerating the planet's descent into a deep freeze. The thriving communities of the warm Ordovician seas faced a catastrophe unlike anything they had ever known. The Hernantian glaciation, as it would come to be called, was a sudden and merciless ice age. As the ice sheets grew, they locked away immense volumes of water, transforming the landscape of Gondwana into a frozen wasteland. The white expanse stretched for thousands of kilometres, a silent, relentless force reshaping the planet. With so much water trapped in ice, global sea levels plummeted by as much as 100 metres or more. The shallow seas that had once covered the continents receded, exposing vast stretches of barren seafloor. Where once there had been vibrant marine habitats, now there was only emptiness. The seabeds, stripped of their life-giving waters, became graveyards of stranded creatures and abandoned reefs. This sudden loss of habitat was devastating. Entire ecosystems collapsed as the foundation of Ordovician life, the shallow seas, vanished almost overnight. Countless species, perfectly adapted to the gentle warmth and stable conditions of the shallow waters, found themselves stranded. Their world was shrinking, their options running out. The extinction that followed came in two brutal waves, each tied to the advance and retreat of the ice. The first pulse struck as the world froze and the seas withdrew. The sudden chill and catastrophic drop in sea level left many species with nowhere to go. The cold seeped into every corner of the ocean, and habitats vanished beneath the receding waters. Creatures that could not adapt to the frigid temperatures or migrate to the few remaining refuges perished in droves. The oceans, once alive with colour and movement, grew quiet. It is estimated that around 60% of all marine genera vanished in this first onslaught, their lineages ending in the cold silence of the Ice Age. Brachiopods, trilobites, corals, and countless other groups that had defined the Ordovician seas were decimated, their once thriving populations reduced to scattered survivors. The intricate web of life that had evolved over millions of years was torn apart. The Ordovician's vibrant ecosystems were left in ruins, yet the story did not end with the cold. In a cruel twist, the climate began to warm once more, setting the stage for a second, equally deadly wave of extinction. As the ice sheets melted, torrents of water poured back into the oceans. Sea levels rose rapidly, flooding the newly exposed continental shelves and transforming the landscape yet again. The seas surged over the land, reclaiming territory lost to the ice. But this was not a simple return to the old order. The returning waters were different, often depleted of oxygen, creating vast, suffocating dead zones where little could survive. This anoxic crisis may have been triggered by changes in ocean circulation or the decay of organic matter that had accumulated during the low sea levels. As the waters mixed and organic debris broke down, oxygen was consumed, leaving behind vast stretches of lifeless, stagnant sea. For the survivors of the first extinction pulse, this new crisis was insurmountable. Many species that had clung to existence through the cold now succumbed to the suffocating, oxygen-poor waters. In the end, the twin catastrophes of ice and anoxia wiped out an estimated 85% of all marine species. The Ordovician mass extinction stands as the second largest in Earth's history, a stark reminder of the power of natural forces to reshape life on our planet. Along the wild, wind-lashed shores of the Ordovician, where the ocean's restless waves battered ancient rocks and fog crept over barren ground, a silent revolution was beginning. For eons, the continents had been nothing but desolate expanses, vast stretches of rock, sand and lifeless soil, untouched by the green touch of life. These lands, sculpted by wind and water, had never known the shade of a leaf or the shelter of a stem. The only sounds were the sigh of the wind and the distant crash of surf. No birds, no insects, not even the rustle of a blade of grass. But in the quiet margins where water met land, something extraordinary began to happen. Tiny green pioneers, no larger than a fingernail, crept from the water's edge, their delicate forms braving the harsh, open air. These were the first plants to ever set foot, so to speak, on solid ground. There were no forests, no towering trees, not even ferns. Instead, the earliest colonists were humble and unassuming, tiny mosses and liverworts clinging to damp stones and the moist soil at the water's edge. These non-vascular plants, ancestors of today's mosses, were fragile and utterly dependent on moisture. They could not stray far from the life-giving water, for their bodies would quickly dry and perish in the open air. Yet their presence is written in stone. Microscopic spores, preserved for nearly 500 million years, tell the story of their first forays onto land. These tiny capsules, scattered by wind and water, are the earliest evidence of life's conquest of the continents. These first land plants, known as bryophytes, were nothing short of revolutionary. They formed soft green carpets along the water's edge, transforming bare stone into living, breathing surfaces. Their world was a realm of mist and dew, where every droplet of water was precious. They clung to the dampest places, river banks, lake shores and coastal wetlands, where the air was thick with moisture and the sun's rays filtered through clouds of fog. For the first time, a living green fuzz began to spread across the rocks and soil, a gentle tide of life inching ever farther from the water's embrace. These simple plants performed a kind of terrestrial alchemy. Through the miracle of photosynthesis, they captured sunlight and drew carbon dioxide from the air. weaving energy from the elements themselves. As they breathed in carbon dioxide and released oxygen, they began to alter the very atmosphere. Their quiet work may have helped cool the planet, setting the stage for the great ice age that would one day sweep across the globe. In this way, these tiny plants became the planet's first living air conditioners, subtly shifting the balance of gases in the air and changing the world forever. But their influence reached even deeper. As they grew and died, their bodies began to accumulate, forming the first thin layers of organic matter on the land. Their root-like rhizoids, though tiny, worked their way into cracks in the stone, prying apart the ancient rocks. Over countless generations, this slow, patient work began to create true soil, a foundation for all future terrestrial life. Their mats held sediment in place, preventing it from washing away with every rain or tide. For the first time, the land began to stabilize, readying itself for the next wave of colonists. In the shelter of these mossy carpets, tiny worlds began to form. Damp microhabitats, rich with moisture and nutrients, offered a safe haven for the first small animals, primitive arthropods perhaps, or the earliest mites, to venture out of the water and onto land. These humble mosses were the architects of a new world. Their green carpets laid the groundwork for every forest, every meadow, every ecosystem that would ever flourish on land. Recent discoveries have revealed even more about this ancient transformation. In the rocks of the Ordovician, traces of these first land plants are preserved, silent witnesses to a world in transition. In what is now Ohio, pieces of fossilized amber, ancient tree resin, have been found, glimmering with the golden light of ages past. This amber hints at the existence of small, bushy plants along the ancient coastlines, tiny microforests that sheltered in the mist and fog, their resin capturing the story of their world. Though these were not forests as we know them, they reveal that life on land was already more diverse and complex than once imagined. The tapestry of green was beginning to spread, thread by thread. The colonization of land was not a sudden leap, but a slow, persistent advance. Over countless generations, the green pioneers crept farther from the water, their numbers growing, their influence deepening. The tiny green shoots of the Ordovician were a quiet promise, a whisper of the vast, vibrant world to come. In their relentless quest to survive and spread, they opened the door to every future forest, every field, and every living thing that would one day call the land home. Our entire understanding of the Ordovician world is built upon the remarkable fossils it left behind. Silent storytellers, locked in stone for nearly 500 million years. Most fossils are just the hard parts of animals, shells, bones and teeth, remnants of trilobites, brachiopods and armoured fish that once thrived in ancient seas. But on rare occasions, extraordinary conditions, anoxic waters, rapid burial and fine sediments preserved even the softest tissues, capturing the delicate outlines of tentacles, gills and eyes. These fossils are like time capsules, offering a complete snapshot of entire ancient ecosystems. Such exceptional fossil sites are called Lagerstätten, a German word meaning storage places. These sites are treasure troves, where the diversity and detail of life are preserved with breathtaking clarity. The Ordovician period boasts several of these windows into the past, each revealing a unique chapter in the story of life. Among the most celebrated is the Fezuata Formation in Morocco, a fossil bed that has yielded thousands of exquisitely preserved creatures. Dating to the early Ordovician, the Fezuata fossils reveal a stunning mix of life: soft-bodied worms, armoured arthropods, and the earliest ancestors of modern marine animals. Here the strange forms of the Cambrian meet the emerging complexity of the Ordovician, bridging two worlds in stone. The Fezuata site is especially renowned for its arthropods, creatures with jointed legs and segmented bodies, preserved in such detail that even their limbs and feeding appendages are visible. Among these is Edurocassis, a giant 2-metre-long relative of Anomalocaris. Unlike its predatory Cambrian cousin, Edurocassis was a gentle filter feeder, gliding through the water in search of plankton. Its elaborate comb-like appendages, preserved in astonishing detail, show how it sifted tiny organisms from the water, a glimpse into the evolution of new feeding strategies in the Ordovician seas. Far across the ancient globe, the Winneshiek Lagerstadt in what is now Iowa, USA, offers another extraordinary fossil record. This 460-million-year-old deposit formed in the quiet waters of a meteorite impact crater, where low oxygen and fine sediments created perfect conditions for fossilization. Here, the fragile bodies of early sea scorpions and some of the oldest jawless fish were preserved, their forms frozen in time. These fossils provide a rare look at the inhabitants of a unique Ordovician habitat, from armoured eurypterids to primitive vertebrates. Each fossil, no matter how small, is a puzzle piece, revealing the anatomy, behaviour and environment of creatures that vanished long ago. In recent years, advanced imaging has unlocked even more secrets. In 2023, three-dimensional X-ray scans allowed scientists to reconstruct the brain case of Apticopsis, a primitive vertebrate from 458 million years ago. These scans revealed that complex brain structures evolved much earlier than previously believed, pushing back the origins of our own lineage. In France, the Cabrieres biota preserves a rare polar ecosystem from a cold, high-latitude Ordovician sea, its fossils telling of life far from the equatorial warmth. The unique iron-based preservation of soft-bodied animals here offers a precious glimpse into the adaptations of creatures living in frigid ancient waters. Even the great extinction event at the end of the Ordovician is recorded in the rocks, where layers rich in fossils abruptly give way to barren stone, a silent testament to a world in crisis. By analysing the chemical signatures in these layers, scientists can trace the rapid environmental changes, shifts in ocean chemistry, temperature and oxygen that swept across the globe. Recent studies of carbon isotopes reveal that massive climate fluctuations unfolded in less than 100,000 years, a geological blink of an eye, yet enough to reshape the course of life. Each new fossil bed uncovered, each new detail revealed, peels back another layer of mystery. The fossil treasures of the Ordovician bring this distant world to life, vivid, dynamic, and ever more real with every discovery. The Ordovician period, though separated from us by nearly 500 million years, is far more than a distant chapter in Earth's story. It is a time that continues to echo through the natural world, its legacy woven into the very fabric of our planet's geology, climate and living systems. Imagine a world where the continents are barren and lifeless, but the seas teem with an explosion of life, strange alien creatures drifting, crawling and hunting in vast underwater realms. This was the Ordovician, a crucible of evolution, a stage for some of the most profound transformations in Earth's history. The scientific significance of the Ordovician cannot be overstated. During these 42 million years, life underwent the great Ordovician biodiversification event, the most dramatic and rapid increase in biodiversity our planet has ever seen. In the depths of ancient oceans, new forms of life emerged at a staggering pace. Complex marine ecosystems blossomed with intricate food webs of predators, filter feeders and scavengers. These networks established the blueprint for marine communities that, despite the ravages of time and extinction, still persist in our oceans today. The Ordovician was also the age when shelly fauna, organisms with hard mineralized shells, rose to dominance. Brachiopods, corals and mollusks flourished, their bodies accumulating on the seafloor over millions of years. These remains, compressed and transformed by geological forces, became the vast limestone deposits that now form the backbone of mountain ranges and the bedrock beneath our feet. These rocks are not mere curiosities, they are silent records of ancient seas, preserving the story of life's triumphs and catastrophes in their layers. The natural significance of the Ordovician extends beyond the creatures themselves. The evolution of early plants, tiny and unassuming, began to alter the global climate. As these pioneering plants colonized the edges of the land, they drew down carbon dioxide, triggering a cascade of environmental changes that would eventually lead to one of the first great mass extinctions. This interplay between life and the planet's systems, between biology and geology, demonstrates the profound interconnectedness that defines Earth's history. In the shadowy waters of the Ordovician, the first vertebrates, jawless, armoured fish, began their journey. Though humble, these creatures possessed the internal skeleton that would become one of evolution's most enduring innovations. Surviving the extinction that ended the period, their descendants would give rise to jawed fish, then amphibians, reptiles, mammals, and ultimately all vertebrate life. The story of every creature with a backbone, from the smallest fish to the largest whale, traces its origins to these ancient seas, where survival meant hiding from giant cephalopods and sea scorpions and adapting to relentless change. The Ordovician teaches us that life is resilient, but also vulnerable. It shows how the shifting of continents and the building of mountains can spark evolutionary radiations, how the rise of simple plants can reshape the atmosphere, and how sudden environmental upheaval can bring even the most successful forms of life to the brink of extinction. The world is dynamic, and life is shaped by both catastrophe and opportunity. By studying the Ordovician, scientists unlock the secrets of ancient climates, mass extinctions, and the origins of modern ecosystems. The rocks, fossils, and chemical signatures left behind are a window into a world both alien and familiar, a world that still shapes the Earth we know today. The Ordovician matters because it is a testament to the power of change, the complexity of life, and the enduring forces that continue to sculpt our planet's destiny. Beneath the ancient Ordovician seas, another force was at work, one that shaped life in ways both subtle and profound. While marine creatures thrived above, the ocean floor itself was a landscape in flux, marked by the restless stirrings of volcanic activity. Across the globe, vast underwater mountain chains erupted with fire and ash. These submarine volcanoes, known as mid-ocean ridges, split the seafloor and poured molten rock into the darkness, forging new crust and releasing plumes of mineral-rich water. In places, colossal volcanic islands breached the surface, only to be battered down by waves and time. This volcanism was not a distant background event. It influenced the chemistry of the oceans, altering the balance of nutrients and oxygen. Volcanic ash settling through the water fertilized the seas with elements like iron and phosphorus. These nutrients spurred blooms of plankton, the tiny drifting organisms at the base of the marine food web. As plankton populations soared, so too did the creatures that fed on them, driving bursts of diversification that echoed through the entire ecosystem. Yet the gifts of volcanism came with risks. Massive volcanic eruptions could cloud the atmosphere with ash and gases, casting shadows over the ocean's surface and cooling the climate. In the deep sea, hydrothermal vents created oases of life, but also zones of toxicity, where only the most adaptable organisms could survive. At times, the release of volcanic gases tipped the delicate balance of oxygen, leading to brief but deadly episodes of ocean anoxia, where vast regions of seabed turned hostile, suffocating marine communities and leaving behind dark, organic-rich shales as silent witnesses to these crises. The interplay between fire and water, between volcanic upheaval and marine life, was a driving force in the Ordovician world. It spurred evolution, shaped extinction, and carved the stage upon which ancient creatures lived and died. Today the fingerprints of Ordovician volcanism are etched into the rocks, layers of ash, hardened lava flows, and the chemical traces of primordial eruptions. They remind us that even in the most tranquil seas, the forces of the earth are never truly at rest. The story of the Ordovician is not just one of life's triumphs, but of its constant negotiation with the planet in motion, a world where fire beneath the waves could both nourish and threaten, driving the endless dance of change that still shapes the oceans today. As the Ordovician seas teemed with life, another silent revolution was unfolding beneath the waves. Tiny, unassuming, yet profoundly influential, early marine plants began to take root in the ocean's embrace. These pioneers of the plant kingdom were not the towering trees or sprawling shrubs we know today, but microscopic algae and simple filamentous forms that floated in the sunlit waters. In the warm, shallow seas, these early marine plants found an environment ripe for colonization. With the sunlight penetrating the clear waters, photosynthetic organisms thrived, converting sunlight into energy and releasing oxygen as a byproduct. This process, known as photosynthesis, was a game-changer for life on Earth. It not only provided a new source of energy, but also contributed to the gradual increase in atmospheric oxygen, setting the stage for more complex life forms to evolve. Among these early plants, green algae were particularly successful. Their simple yet efficient cellular structures allowed them to harness sunlight effectively, spreading rapidly through the marine environment. As they multiplied, they formed vast green carpets that covered the seafloor, creating new habitats and food sources for marine animals. These primitive plants anchored themselves to rocks and shells, stabilizing sediments and preventing erosion, which in turn helped to create more stable environments for other organisms. The spread of these early marine plants had far-reaching impacts on the Ordovician ecosystem. By producing oxygen, they helped to oxygenate the oceans, supporting the growth of aerobic life forms. Their presence also led to the development of complex food webs, as herbivorous animals evolved to feed on them, and predators then evolved to feed on the herbivores. This cascading effect of plant life on the marine food web drove a surge in biodiversity, contributing to the Ordovician radiation, one of the most significant evolutionary events in Earth's history. But the influence of early marine plants extended beyond the biological realm. As they photosynthesized, they absorbed carbon dioxide from the water, playing a crucial role in regulating the Earth's climate. This carbon sequestration helped to moderate global temperatures and contributed to the drawdown of atmospheric CO2, which may have played a role in the onset of the Ordovician Ice Age. Today, the legacy of these early marine plants is preserved in the fossil record. Ancient stromatolites formed by layers of algae and microscopic fossils of early phytoplankton provide a window into this transformative period. They serve as a reminder of the profound impact that even the smallest organisms can have on the planet, shaping the environment and driving the evolution of life. The story of early marine plants in the Ordovician is a testament to the power of photosynthesis and the interconnectedness of life. It highlights how the simplest forms of life can set in motion a chain of events that transform entire ecosystems, paving the way for the complex and diverse world we inhabit today. Beneath the restless waves of the Ordovician, A hidden transformation was unfolding, one not of creatures or plants, but of molecules and minerals. The chemistry of the world's oceans was in flux, and these subtle changes would shape the destinies of all marine life. At the dawn of the Ordovician, the seas were rich in dissolved iron and other minerals, their waters tinged green by the abundance of these elements. Oxygen, while present, remained relatively scarce, confined mostly to the uppermost layers where sunlight could reach and photosynthetic organisms could thrive. Below, in the shadowy depths, anoxic conditions prevailed. Here, ancient chemical cycles churned, driven by volcanic activity and the slow weathering of continents. As early marine plants and cyanobacteria multiplied in the sunlit shallows, their relentless photosynthesis began to tip the balance. With each pulse of sunlight, oxygen was released into the water, gradually increasing its concentration. This oxygenation was not uniform. Localized oxygen oases formed near dense mats of algae, while deeper waters remained starved of this vital gas. The rising oxygen levels triggered a cascade of chemical reactions. Iron, once freely dissolved in the water, now began to react with the newly available oxygen, precipitating out as rust-colored sediments on the sea floor. These iron formations, preserved today in ancient rocks, mark the growing influence of life on Earth's geochemical cycles. Calcium and carbonate ions, too, played a pivotal role. As marine organisms like brachiopods and trilobites built their shells and exoskeletons, they drew these dissolved minerals from seawater, locking them away in limestone and other sediments. The chemistry of the oceans shifted, with carbonate platforms expanding and vast reefs rising from the sea floor, each a monument to the interplay between biology and geology. But these chemical changes were not always gradual. Episodes of volcanic activity spewed ash and nutrients into the seas, altering their pH and mineral content. Weathering from newly exposed land masses added fresh supplies of phosphorus and other essential elements, fueling further blooms of life and further oxygenation. By the end of the Ordovician, the oceans had been fundamentally transformed. Oxygen had become more abundant, iron had been largely stripped from the water, and the stage was set for the evolution of even more complex life forms. The chemistry of the seas, once dictated by geology alone, was now inextricably linked to the actions of tiny, photosynthetic pioneers. In these ancient waters, the invisible dance of elements and molecules forged the conditions for life's next great leap. The story of the Ordovician oceans is a story of transformation, not just of species, but of the very substance of the sea itself. Beneath the sunlit ripples of the Ordovician oceans, a silent drama unfolded. A perpetual contest between hunter and hunted, shaping the very fabric of early marine ecosystems. Here, in the cradle of ancient seas, the rules of survival were being rewritten, one pursuit at a time. The trilobites, armoured and agile, scuttled across the seafloor in search of algae and detritus. Yet their shield-like shells were more than just protection. They were a response to the ever-present threat of predation. Above them glided the nautiloid cephalopods, the era's most formidable hunters. With long conical shells and a ring of tentacles, these ancient relatives of the modern squid hovered with a ghostly grace, their keen senses attuned to the faintest movement below. Every encounter was a test of evolutionary arms. The nautiloid's sharp beak and jet propulsion allowed for swift, targeted strikes. Trilobites, sensing the disturbance, would suddenly enroll, curling into tight armoured balls, their vulnerable undersides safely hidden. Sometimes these defences held. Other times the cephalopod's beak found its mark, piercing shell and ending the chase in a silent cloud of silt. Elsewhere, the world's first jawless fish, the ostracoderms, filtered particles from the water, wary of swift-moving arthropods like eurypterids, the so-called sea scorpions. Armed with spiny pincers and a predatory instinct, these eurypterids patrolled the shallows, their armoured bodies glinting in the filtered sunlight. When prey was spotted, they lunged with rapid jointed limbs, snaring smaller creatures in a sudden embrace. But even the hunters were not invincible. Giant orthocones, some growing several metres long, dominated the open waters. Their size alone made them nearly unassailable, yet competition for food was fierce. Swarms of filter-feeding graptolites and planktonic larvae drifted in the currents, providing a feast for those swift enough to seize them, and a challenge for any predator hoping to outpace the competition. This relentless cycle of adaptation and counter-adaptation drove the evolution of new defences, thicker shells, spines and burrowing behaviours. It also inspired new hunting strategies, stealth, speed, and in some the first hints of complex vision. In these primordial seas, life was both creator and destroyer. Each encounter, each narrow escape echoed through time, fueling the diversity and complexity of marine ecosystems. The predator-prey battles of the Ordovician seas were not just struggles for survival. They were the crucible in which the future of life was forged. One chase, one escape, one adaptation at a time. As the Ordovician period drew to its close, the vibrant tapestry of marine life faced an unprecedented reckoning. In the deep silence of ancient oceans, the stage was set for one of Earth's earliest and most devastating mass extinctions, a cataclysm that would erase nearly 85% of marine species in just a few million years. The first whispers of disaster began with a global chill. Across the planet, temperatures plummeted as massive ice sheets crept over the southern supercontinent Gondwana. Sea levels dropped dramatically, exposing vast stretches of shallow continental shelves, the very habitats where life had flourished most abundantly. Reefs and thriving seafloor communities were left high and dry, their delicate ecosystems shattered by the relentless advance of ice. Beneath the waves, the chemistry of the oceans shifted. With the cooling climate, oxygen levels in the water plummeted. Stagnant anoxic zones spread across the seafloor, suffocating countless species, trilobites, brachiopods, graptolites and corals, all victims of the silent, invisible change. The once bustling reefs fell silent, their builders and inhabitants lost to the deep. But the crisis didn't end with the cold. As the ice sheets eventually melted, sea levels surged back, flooding the continents once more. The sudden influx of fresh water disrupted ocean currents and further altered the chemistry of the seas. This rapid shift triggered a second wave of extinctions, as species already weakened by previous losses struggled to adapt to the new, unstable world. Throughout these upheavals, no single cause stood alone. Instead, a complex web of climate change, sea level fluctuation and shifting ocean chemistry combined to unravel the intricate balance of life. In the end, the Ordovician extinction events reshaped the very fabric of the oceans, clearing the way for new forms of life to emerge. Yet, from this devastation, the story of evolution pressed on. The survivors, those few species resilient enough to weather the storm, would become the ancestors of future lineages, their legacy written into the rocks and fossils of a changed world. The Ordovicians' great dying was not just an ending, but a dramatic turning point in the ongoing saga of life on Earth.